Oh, absolutely. You need a projector? No. Good. We'll hang around afterwards also if you have any questions, and you can always get a hold of me. We do many talks throughout the months, each month, so just let us know.
All right, everyone. Hi, my name is Nick Morzowski. Thank you all for coming today. And thanks to Protecting Tomorrow and AIS for giving us this bigger space because we're running out of room at the other location. Glad everyone was able to make it okay. I'm really excited to be here tonight because I'm amongst my fellow robot people. It doesn't always happen. So it's exciting to talk to you guys. Before I get into my talk, I want to give a little bit about my background. So I think it all started with my first Lego set as a kid. It was all kind of downhill or uphill from there. I grew up in the Bay Area, but then I went to Carnegie Mellon in Pittsburgh to do my undergrad in mechanical engineering and robotics. And so being able to take some cross-listed robotics courses with grad students was a really great experience to see this whole world. I graduated in 2007 and moved to San Diego to work at Hewlett-Packard in Rancho Bernardo. I was working as a systems engineer on inkjet printers. In 2009, I went back to school, grad school at UCSD, focusing on dynamics and controls within mechanical engineering and research in mobile robotics. In addition to academic research, I also was lucky enough to consult with multiple companies developing commercial and consumer robots. Since defending my dissertation last fall, I've been doing consulting practice with companies here and around. All right, so here's the outline of what I'm going to talk about. I'm going to try to keep it quick. I'm probably going to skip a couple slides so we have a little bit of time for Q&A at the end. I think that'll be good. So I'll start with just kind of an introduction of what I kind of see going on in the robotics space and trends and hardware. Then get into some of the tools that I think have only recently been available but make prototyping robots and hardware a lot easier and faster than they were previously. There's a couple leftover math-heavy slides from my dissertation, but I'll probably just kind of breeze through those. I'll also talk about two specific robots that I brought today. So Switchblade is a treaded multi-purpose ground vehicle, and then Skysweeper is a high-wire locomoting robot. And we'll see more about that. And then to conclude, I have a set of rules that I've developed that have been kind of rules of thumb for developing robots that I hope will be very useful and practical for you guys. So, introduction. There is a hardware revolution underway, and robotics is a subset of hardware. But depending on your definition of a robot, the hardware that's being developed right now by startups and companies, it's not purely mechanical. It's not even just electromechanical. There's code running on embedded processors. People aren't just making better mousetraps, or if they are, it's a robotic mousetrap. So this particular one was featured in Make magazine. It just has an Arduino that monitors a proximity sensor, and if a mouse crosses the path, it uses an electromagnet to drop the basket. That's not technically a robot. I don't know what is. The barriers to entry in developing hardware and robots are plummeting quickly. I think this is largely driven by low-cost capable components, software tools, and global communications. For would-be startups, this is both a challenge and an opportunity. It's a lot easier to get into the space, but how do you create value in a unique way and avoid just being commoditized and lost in the noise? Finally, the line between hardware and software is being blurred. When I bought a GoPro last year, I opened the box, the first thing I noticed was a notice that says, you must immediately update the firmware, otherwise it will not work. So for companies, that makes things a little bit easier because you can ship the hardware first while you're still trying to debug the software and then push out a software update later. What the hardware can do is really a function of what software is on it. The other obvious example is smartphones, that everyone buys a communications device, then you download other apps and you enable completely different functionality. Talking more about this proliferation of low-cost and capable microprocessors and sensors. So 3D Robotics CEO Chris Anderson likes to use the phrase the peace dividend of the smartphone wars. meaning that when all these big global companies, Apple, Samsung, and Google, were fighting to get in our pockets, they were driving the cost of technology and sensors like accelerometers, gyroscopes, magnetometers, light sensors, cameras, GPS, Wi-Fi, Bluetooth, you name it. All of those prices dropped significantly and capability went up, which means that all of us get access to those technology in a way that just wasn't possible 5-10 years ago, at much lower cost. Of course, the other side of that has been from the bottom up with the maker movement, especially Arduino and those guys in Italy who wanted to bring programming to artists. And we're all benefiting from that too, and this focus on ease of use and those communities that build up around those products. Another, I think, critical example is additive manufacturing or 3D printing that has dropped orders of magnitude in price in the last few years. This has made it for people like us much easier to do rapid prototyping right on your desk, again, increasing that cycle, lowering that barrier to entry. So I stole this slide from Cyril Abelweiser's great deck on hardware trends. He's in charge of the Hackcelerator, the Shenzhen-based incubator for hardware. And so he kind of splits up the ecology of hardware people this way. Makers who build for fun, education, goodwill. Maker pros who turn their hobby into a business, often creating tools for other makers. Inventors who invent and sometimes license their ideas. And hardware startups were born to scale, meaning that they're not trying to do a one-off type project, but the eye is on making thousands, millions of products. And that means that as you're developing your work, you have very different constraints to work under. Naturally, there's a lot of gray area and overlap, and you're not necessarily in exactly one bin. Just kind of out of curiosity, how many people would characterize yourself as a maker? First category? Maker pro? Inventor? A hardware startup? Cool. Yeah, and there's no right or wrong. These are all right answers, and usually people travel along this path. And the rate at which you can move along is getting faster and faster. So I want to talk about a few challenges that I see in robotics. I think three of the main issues are perception, mobility, and manipulation. And so, of course, they have overlap. And so I tried to put in some examples. So perception issues would be localization and mapping. Mobility, things like doors and stairs for trying to navigate human environment or unstructured terrain. So in unstructured terrain, the perception really comes into play. You need to identify what obstacles there are in the path. Finally, manipulation, picking things up, moving them. Obviously related to perception, you have to know where to pick up an object. So for things like sand and eggs, very different techniques to try to manipulate those. And related to mobility, if you need to open a door, you have to figure out how to manipulate the door handle in order to get through. And so I think the canonical problem in robotics is at the very center of these, which is go get me a beer from the fridge. You have to be able to navigate to the kitchen, maybe go upstairs or downstairs, find the fridge, open the fridge, locate the beer, pick it up, backtrack. It's an incredibly difficult problem. People like to think that it's just around the corner, and if you look at sci-fi movies, it seems like it should be relatively simple, but it's actually a very difficult problem. It's comprised of many different parts. So in my academic research, I focus mostly on the mobility problem, partially looking directly at stairs. All right, next I want to talk about some tools that we all have available to us now. So starting with mechanical engineering tools, I don't think I have to extol the virtues of 3D printing to this crowd. But the good news is that multiple materials are here and more are coming. So as an example, NinjaFlex, or there's a few other flexible filaments. So that gets interesting that you don't have to just design rigid pieces that screw together, but also as multi-material printers, that is, printers with more than one head printing different types of materials come together, you can make much more complex structures printed monolithically all at once. And of course, printers are only getting faster and faster as well. So this is a really exciting time to be able to build physical things. There's also a new generation of CAD tools available. So for example, Tinkercad, which is really targeted towards the novice or the student in kind of an education space, is a very simple to use tool designed to let people get in manipulating objects and downloading them and 3D printing them. Of course, it's somewhat limited in its scope, but if you start there, there's many more tools to go with. Another really interesting one is OpenSCAD, which, sorry, which targets programmers. It's a text-based CAD tool, so you define objects with commands like cube, cylinder, sphere, translate, rotate, mirror. And so combining those, you can get really complex geometry. I think the really interesting thing there is you can parameterize, so you can set a value at the beginning of your file just like you would have an input argument to a function call. And the cool application of that is the Customizer app on Thingiverse, where you can upload customizable phone cases and you choose what model of phone you have, you choose what design you want on the back, and then the OpenSCAD backend from those parameters automatically computes the 3D geometry to fit those, and then you download the file and 3D print it. Very interesting paradigm. The next one I want to talk about is Onshape, which is fairly new. The team is the original team behind SolidWorks, and so if you use SolidWorks, you'll recognize their interface, but it's totally cloud integrated and browser based. It's all in your browser using WebGL, not unlike Tinkercad, but it's much more high-end, designed for power users, professional users. However, it's free for personal use, and only $100 a month per user for professional use. And so unlike SolidWorks with the $5,000 upfront payment, you just have the monthly. The interesting way that they differentiate between personal and professional is that if you want your documents to be private, you have to pay for that. So pay for private model. With the idea being that if you're sharing everything in kind of the Maker or Maker Pro category, then you want to be sharing with the community and getting feedback. But if you're building a business and selling something, you probably want to keep that private at least until the product is launched. So it's an interesting way to differentiate that we haven't seen before. Moving on to electrical engineering tools. So I think a very common one is EagleCAD, and they have a free version, a very low-cost hobby version that they're definitely targeting the makers and the Maker Pros. SparkFun and others offer libraries of components. So an interesting paradigm is that if you're prototyping with breakout boards of various components from SparkFun, and then you're ready to integrate everything into your own circuit board, you can just take those circuit diagram schematics and put them all together, and it's much faster. So this hardware, software comes together, and that you buy this physical thing, but you also get the virtual instance of it that you can mix together also. Fritzing is another great program. It has a unique breadboard view that you've probably seen here on various Instructables. So like Eagle has a schematic view and a circuit board view, Fritzing has this breadboard view, and you can switch between the three, defining your connections. So this helps to bridge that gap between when you're prototyping something on a breadboard to when you actually want to go and produce that circuit board. So again, software tools that are accelerating the iteration cycle for making electronics. Lastly, I want to mention Circuit Maker, which is powered by Altium. So it's another example of a company trying to jump on the Maker bandwagon. So they took some of the engine from their Altium Pro level software and put it in a free Maker level software package called Circuit Maker that has one of their kind of killer features is built-in 3D that you can auto-populate a 3D model that you could then put into your CAD model as you're building an enclosure for your circuit board. And they also use this pay-for-private model. So for free, everything is public, again, to try to entice more people to join on, but if you want to do something you want to keep private, then you have to pay for that service. I think we're going to start to see that pay-for-private model coming out more and more in web services. The last thing I want to mention, kind of going back to 3D printing, but now combining mechanical and electrical. I suspect many of you have seen the Voxel 8 3D printer that was announced at CES that combines a traditional FDM printer with a conductive silver ink that you can build in circuits into your physical builds. And so this is still a very early stage. They had just a dead simple example. If you plug in a USB stick and it turns on an LED. They also had an example where you print a quadcopter and it automatically lays the traces to connect the motors to the circuit board. But this is still very basic. But if you use your imagination and think forward a couple years, you could imagine that we could start printing transistors. And then at that point, you could look to Moore's Law, and the size of those transistors would keep decreasing and decreasing. And you won't be going to Thingiverse to download an Arduino case. You'll be going to Thingiverse to download an Arduino processor core that you then print out inside of your robot. So this is really interesting first steps into fusing mechanical and electrical. There's a lot of great software tools out there. There's an explosion of single board computers. I'm sure pretty much everyone in the room has either used an Arduino, Raspberry Pi, Beaglebone Black, some combination of them. Those are probably the three most popular ones right now. And really the value is not just in the board, but the value is in the community that produces droves of example code and provides free support on forums and sharing of information that really makes it faster to develop. If there's some sensor or actuator you're trying to interface with, chances are someone's already done it and shared their code online. So that, again, makes it very fast to develop and iterate products. One note on that, pay attention to licenses. There are several different open source licenses out there. Open source isn't always open source. Read the fine print on the Creative Commons licenses, and be a good community member too. If someone posts some share-alike IP, if you develop off that, share it at the same license. Enjoy that karma. If you put it out there, it'll come back to you. Another interesting hardware platform is Spark. They are really focused on the Internet of Things type applications where they have a single board computer with built-in Wi-Fi module, or they just announced a built-in 2G or 3G cell radio. They've got a Kickstarter going on right now. And they, let's say, leverage the language of Arduino to make it very simple to use. So if you have experience with Arduino, you can program on their platform using the exact same syntax. So again, these tools make building products much easier. There's now a number of projects that have been built with that Kickstarter project that have had their own Kickstarter project. So we're seeing this feedback cycle. Finally, for a little more complex software-driven robots, robot operating system, ROS, of course, is important to mention. I think there have been talks about that in the meetup in the past, so I'm not going to dive too much into that. But one thing I've noticed is that it has so powerful modules for dealing with things like laser scanners and complex mapping and navigation algorithms. But if you're trying to do very low-level real-time control, some of the communications can be a little bit of a bog down. So just be careful if you're trying to implement some of that real-time stuff with ROS. So those were kind of the engineering tools, but I also want to talk from an economical standpoint about how do you fund. If you're trying to move up to Maker Pro or being your own hardware startup, how do you do that? It's really interesting because of these tools, it's much faster, and so the ability to bootstrap your own startup that is self-fund has been much easier to do recently because it's cheaper and faster to develop these hardware products. So part of the cost is in actually buying the hardware software licenses, but a large part of your cost is actually your time, your opportunity cost that you could be spending otherwise. But now that you can develop faster, that cost is significantly reduced. So you can afford to do multiple iterations of prototypes before you go out and seek angels or investors and have to give up some equity or some control. There's also an increasing number of hardware-focused accelerators and incubators, of course, including the new Qualcomm Robotics Accelerator here in San Diego. This is exciting to see. There's also Accelerator in China, Bolt, based out of Boston, and Highway 1, Northern California. Also, web platforms like AngelList and F6S have popped up to kind of fill that gap to connect startups and VCs. Here's another slide I stole, but even one step below accelerators and incubators, the explosions of hackerspaces, tech shops, fab labs, and even meetups just like this one are helping to build communities where you can find your co-founder and you can work with them and you can get access to tools and makerspaces even before you get into, say, an actual accelerator or incubator. So there's tools and communities that really help this movement of building and developing hardware and robots. Of course, one of these tools is crowdfunding, but just posting on Kickstarter does not guarantee success. You've probably seen them too, but I can't tell you how many projects get posted up, are expecting $30,000 and get $1. It's a bit of a sad story, but I think there's a disconnect because it's a binomial distribution of projects that post on Kickstarter. That means there's two main groups. There's those that are completely prepared, so let me skip ahead a little bit. And so very few campaigns that are wildly successful are overnight successes. there's a lot of pre-work that goes into it. You have to build your community, talk to media, talk to your family and friends, build that up before you launch. If you're not sure if you're ready to launch your Kickstarter, you're not ready to launch. You want to have your community already established. You want to have your mailing list set. You want to know several people you can already count on to contribute, even if it's just at a $5 or $10 level, to help build that buzz and share that. Cyril makes the point that people don't go on Kickstarter and find projects and donate to them. What happens is once you have the project live, it's really the media that picks it up, and that's what gets shared socially. So as the project creator, it's your responsibility to go out, find that media, somehow convince them to cover your project, and you want to start that process before it launches. Once it goes, you've got 30 or maybe 60 days. That's very little time. You want to have everything in place. So getting that media momentum is important to get that exposure. It's Kickstarter basically just sits back and takes in the money for hosting the platform. They've got a great business model, and if you want to have success there, you've got to bring the audience to Kickstarter. So again, often campaigns have already raised some amount of funding, either from friends and family or angels or other investors, to really nail the crowdfunding campaign. But there's also a risk in that you need to do your market validation work prior to launching. If you're not sure if there's a market for your product, then it's not time to kickstart. You need to know that there are people who are willing to put out for it before you put it out there. Otherwise, you may be these poor folks who were expecting $30,000 and got $1. Also, these people were trying to run 2 campaigns at the same time. That's just not possible. If you're trying to run a major campaign, it takes all of your time. All right, so those are kind of the slides I had on general tools. I've got a couple tactical details of specific hardware, software things that I found really useful in my work, so I'm going to try to cover those quickly, but not taking up too much time. So in my research work, I did a bunch of balancing robots. So maybe some of you have seen MIP, the little toy robot by WowWee that we co-developed at the Coordinated Robotics Lab. And so this guy has balancing algorithms built in, accelerometers and gyroscopes, so he can keep his balance. Better catch him. Thank you. And so I just wanted to share some tactical details that these MEMS, accelerometers, and gyros that we all have in our phones can be used for cool applications like this, but the sensors aren't perfect. So if you have an accelerometer, it tends to have high frequency noise. So you may think optimistically that it's an accelerometer, it measures acceleration. Well, I know math. If I integrate the acceleration twice, I can get the position. But that is hopelessly optimistic. It turns out there's so much high frequency noise that if you try integrating that twice, you just get junk. So that approach with these consumer level sub $1 sensors is not feasible. But for things like measuring your angle, you can measure the gravity vector, and you get a pretty good measurement of that. But if you're moving very quickly, then obviously there's body accelerations that read into that too. So measuring the angle that way just gives you a low frequency measurement of the gravity vector. But now you can add in your MEMS gyroscope, which is good at measuring rotational velocity. And okay, I know math, I can integrate my velocity to get position again, but you run into similar issues with thermal drift and numerical integration error. Again, now you have a high frequency estimate of position with respect to gravity. So if we have a low frequency estimate and a high frequency estimate, there's got to be some way to put them together. Turns out there is. It's called a complementary filter, where you apply a low pass filter to the accelerometer to get rid of all the high frequency noise. You apply a high pass filter to the integrated gyroscope to get rid of the low frequency offsets and integration error. Choose the constants so they sum to 1, put them together, and now you have a very solid estimate of the angle with respect to gravity. Some of you may have also heard of Kalman filters, which are, under very certain circumstances, optimal and the best. But if you don't know what you're doing with the Kalman filter, it's very easy to make it suboptimal. Actually, almost guaranteed to make it, because these types of sensors don't have ideal noise characteristics that Kalman filters typically assume. Moving on. Encoders. Anyone used encoders? All right, yeah, they're great, but again, they're not perfect, and they're limited by the encoder disk resolution and the clock frequency you have available to sample it. So if you're trying to measure high speed, you have to make sure that your clock frequency is going faster than the encoder ticks are coming in. But if you're trying to measure low velocity, you have to make sure that the encoder ticks are coming in faster than your clock frequency. Otherwise, you just know that you're going slow, but you don't know how slow you're going. So one way to improve upon that is to use quadrature, where you have an encoder with two channels that are offset by 90 degrees. And so again, doing some more math, you can increase your resolution by a factor of 4, and you also know if you're going clockwise or counterclockwise, which is pretty important if you're trying to balance upright. But if you're trying to measure ultra-low velocity, which is what I was trying to do with this project that I'll talk about later, you get into issues where these square waves aren't ideal, and they're not exactly 90 degrees out of phase, and the high time is not exactly equal to the low time. And you need to start looking between subsequent rising or falling edges of different channels. And so there's some advanced things you can do with FPGAs, so super high-speed clocks, to get higher resolution. If you're interested in that, talk to me after, but I'm going to keep moving. Now, another tool I want to talk about is Lagrangian dynamics. And this is a really powerful dynamics formulation that does take some advanced math, but it's worth it in the end. So just like, if you know Newton's second law, F equals ma, force equals mass times acceleration. That's a way of formulating dynamics, or equations of motion. So writing equations that describe how a body, how a system, how a robot behaves. Another way to formulate that equation of motion is using Lagrangian dynamics. And it starts with a simple equation, the Lagrangian L equals the kinetic energy minus the potential energy. I'm not going to go into the details, but many partial derivatives later, you end up with a set of equations that directly describe the behavior of your robot. Now you can take these equations, plug them into a simulation, fiddle with parameters so you can see if I have a 4-kilogram robot or a 6-kilogram robot, how will that affect the performance before actually building the darn thing. You can also use this to identify equilibrium manifolds. So in case of balancing robots, intuitively you think, okay, it can balance only when the center of mass is directly over the contact point. But if you have a little bit more complex system, like this treaded robot, it can balance here, again, where the center of mass is directly over the contact point. But if the angle between the body and the treads changes, that the angle of the body also changes. So you have a manifold, a range of spaces where you can balance. And so you can characterize that and use that to design your controller to keep balance or perform other operations. Again, more math. So even if you have nonlinear dynamics, you can linearize them with more partial derivatives. Stay in school, do lots of math. And then get controllers out of that. And the trick is that all this complicated math, you end up with a very simple formulation, this bottom line here. It's just a little bit of matrix math that you can implement on a real-time controller in something as simple as an Arduino or something more advanced. And so if you do your kind of homework ahead of time where you really know the dynamics of how the system works, you can build that intelligence into the controller that's very simple and implement on a low-power microprocessor. So now I want to get into some details of this first robot. So it has, so much like any other tank robot, it has these powered treads, but uniquely, these tread assemblies can pivot with respect to the central chassis, which significantly changes the center of mass. And so that enables different modes of locomotion. So a basic tank differential drive, where you can balance on the near end in kind of a V, balance on the far end in kind of a crude C, and actually the chassis is shorter than the tread, so it can rotate continuously 360 degrees. And so there's a camera inside here, and so you don't need an additional pan tilt mechanism, because that's built into the robot. Finally, an interesting maneuver, what we call perching, where it can actually balance on the edge of a stair. And so again, the center of mass has to be kept directly over the contact point. So as it drives up, it changes the angle of the body to maintain the overall center of mass directly over the contact point. Got some video on that I'll show in a little bit.
I have to interject here. This was so cool. I told you it was with the fire service. We actually teamed up with their group at UCSD with Professor Bewley and put in a National Science Foundation proposal to convert this kind, adapt this kind of robot for firefighting applications. So cool stuff, man. Think about ways to work together.
Great, yeah. Yeah, so applications, fire response, search and rescue, border patrol, mine exploration, basically anywhere that you don't want to put a human, and you could put a robot. And the unique advantage of this platform is that it's a relatively small robot because it can fold down, but it can still get over relatively large obstacles because it can control its own center of mass and dynamics. When the center of mass is higher, it's easier to climb larger obstacles. And just to note, this is patent pending. So now I want to talk a little bit more about that perching problem, so balancing on the edge of the stair. And not going to dive into the math, but again, if you do all this, it enables you to develop quicker because you can iterate on different types of motors, different sizes of components in simulation without going through the process of actually building and testing the real thing. So it turns out that frictional losses are really important in the system, so it took some good effort to accurately put that into the model and build a controller around that. Talk more about the mechanical design. So inside the robot, the thing that enables these types of maneuvers is a 2 degree of freedom hip joint, where two independent torques are transmitted coaxially along the same line. So the motors, the encoders, and the batteries are all in the main chassis. And then the two torques have to be transmitted along this point, one to rotate the tread and one to rotate the tread assembly. So the tread motor drives the shaft that is coupled directly to the sprocket, but then the second motor on top drives this gear, which is bolted to the tread assembly, but spins freely relatively to this shaft, giving that second independent axis, while keeping everything on one side of the joint. So this greatly simplifies wiring, because trying to put wires across rotating joints, especially continuously rotating joints, is notoriously difficult. So as I was building this robot, I was going through my laser cutting phase. And so almost all the parts are laser cut out of Delrin. So put a giant sheet of plastic into the laser cutter, hit print, wait a while, and then get all your pieces out, and then put them together with interlocking tabs and slots like Lego. And that made everything faster. We ended up making 13 of these robots, and so I was able to employ some undergrads to help build all those too. So here's a video of what it can do. So this is at UCSD. So it's pretty quick. It's about 2.5 meters a second. And so because of its body geometry, doing a curve or single stair is really trivial to do, because it can just lift its center of mass over the edge. And as it tips over, then it gets on that end. You can balance in a V. And then so at this point you can drive it around just like you would anyway. And you can also dynamically change that V angle. And to transition into the other balancing mode takes a few more steps in between. So this is an animation of the stair climbing maneuver. So it approaches the edge of the stair in that C configuration, but then it tilts the chassis over until the overall center of mass in black there is directly over the edge. As it drives up, it tilts the body back to keep the center of mass directly over the edge. So this is a test just balancing on a balance beam. And so this is with a friction compensator controller element turned on. As I mentioned, friction turned out to be a major issue with this. So without the friction compensator, you can see there's more oscillation. So here it is moving forward 10 centimeters. And so at 10 degrees of inclination, and as it does, it tilts that body over to keep the center of mass directly over the contact point. So as I was working on this, I really found the limitations of this hardware platform that were the mass distribution and the friction. And so what happened was that in order to move all the way across the beam, because the center of mass of the body was relatively close to the rotation point, the treads had to be at a very steep angle in order to move the mass over that range. But if your treads are at a very steep angle, that means your normal force at the stair edge is very high. If you have very high normal force, that means you have very high friction. You have very high friction. That means that takes up most of your motor torque, and you don't have as much torque available to drive. Also, you're driving up a steeper slope, takes even more torque, and you're trying to regulate. And so there was a physical limitation of this robot, of this particular build, not necessarily its architecture, that limited to a lower slope. And so in the plots, especially on the bottom, you can see the oscillation, which is when it goes into and out of stiction. So always be aware of friction.
So the friction compensator is a calculation.
Right, it's
something you're doing in the computer.
So it's happening on board the robot, and so based on the direction that the motors are trying to move, and if it's actually moving, it applies an additional torque to help overcome that friction. All right, next I want to talk about Skysweeper, trying to be a little quick here. So this robot has two identical links that are pivotally connected in the middle with what's called a series elastic actuator. What that means is that there's a motor on the side. The motor drives a shaft that's connected to two springs. And so if the motor drives one way or the other, it pushes on one or the other spring. So if you move slowly, it stays in sync, but if you start going quickly, you can see it gets out of phase, so it adds some interesting dynamics to the system. It also allows you to store some potential energy in the spring, and I'll talk about that in just a second. On either end is a three-position clamp. It can either be fully open, that can pass through a cable. It can be partially closed, but it can still roll along a cable, or fully closed, where it can only pivot along a cable. And so if you concatenate those three behaviors and the hub motor, you can get a few different interesting behaviors. So the first is called inchworm for obvious reasons. So if you have one pivoting clamp and one rolling clamp, and you use the hub to open and close, you can translate along the wire that way. Another maneuver is a swing up. So if you start with only one link on, you can rock back and forth until the second link comes up and grabs. And so this is useful if you're trying to get it up on the rope in the first place. You just have to get one side up. The last maneuver is called backflip. So here, you can imagine if there's some obstacle on the cable, say something that's actually physically holding the cable that you can't inchworm across, you can backflip around it. And so that means the obstacle just has to be smaller than half the size of the robot. And of course, this could scale up too.
How do you aim so you don't miss?
So the way the clamp is designed is to align along the axis of the cable. But yes, mechanical, and high winds would be a problem. All right, so again, more dynamics work, and so the way I was able to generate those animations was using a physics-based model, and so not just imagining how it would look, but putting that in, and then I can play with different lengths of the link, try different motors, see what worked. The control is implemented as a finite state machine, where each state is just the control input to the motor and then what position the clamps are in. And the transitions between the states are defined by sensors that measure the angle of the hub, and also sensors that detect if there is a cable present in either clamp. And so this structure was simple enough to implement in an Arduino, which is just mounted on here, then very fast to prototype. On the design, it's almost entirely 3D printed with some off-the-shelf polycarbonate tubing, just because that would take longer to print that, so it's easier to do that off the shelf. Each clamp has a hobby servo that drives these coupled gears to open and close the arms symmetrically. The arms have these rod ends to maintain alignment, and then magnets inside so that they maintain alignment when they're closed, and an IR emitter and a photodiode to detect when a rope passes through. In the hub, it's a simple DC brush motor and two unidirectional torsional springs. Finding two unidirectional torsional springs is easier than finding a bidirectional torsional spring. And built-in potentiometers to measure the angle. All right, so here's a video of the inchworm maneuver. I'm going to skip over the plots. Here's a video of the swing-up maneuver. This is in real time. And in glorious slow motion.
Can it detect and react on this?
So it only closes the clamp when it detects that a cable passes, breaks that light beam between the IR emitter and transmitter or receiver. And so it continues rocking back and forth until it grabs.
All right, and here's the backflip maneuver.
And so you can probably see there's a delay between when it crosses the cable and when it actually closes. That's an artifact of using off-the-shelf hobby servos that have a black box controller that you can't mess with. So be careful of how easy it is to use off-the-shelf components. You're gonna pay one way or another. All right, I'm gonna try to wrap up so we have some time to talk, but these are my rules of robotics. Number 1, never disassemble a working robot. So as a corollary to this, always have a demo ready. You never know when someone's going to come by and want to see that may turn into a good partner, co-founder, investor, who knows. Always have a demo ready. And similarly, video or it didn't happen. It makes it a lot easier to share. Actually, along this lines, YouTube is a huge community. There's lots of people who post robots, videos of their robots. Actually, another grad student in my lab would post videos of his projects, and he was contacted by IHMC, which is a robot institute in Florida. They were, I think they got 2nd place in the DARPA Robotics Challenge last year, and he got a job through his robot YouTube channel. Wow. So don't underestimate the power of sharing your work and getting feedback. All right, number 2, if it works the first time, you're testing it wrong. Statistically, that's probably it. And then about testing, you get to this point where how good is good enough? And so from the start of the project, have defined metrics. How will you know if it's working? Does it just look right, or is it actually performing certain tasks in a certain amount of time? Helps to define those sooner than later. And related to that, if you can't measure it, you can't control it. And there's a whole body of theory about observability and controllability that we can get into later, but as an engineer, if you can't measure it, how are you supposed to control it? Number 3, when in doubt, lubricate. So that's a little bit stolen from Jamie Heineman of Mythbusters, but it's often true in robotics too, especially if you have mechanical moving linkages. Don't neglect that. And of course, even if you lubricated it 6 months ago when you first put it together, it probably needs to be cleaned out and relubed. All right, number 4, never underestimate the estimation problem. So this is saying that it's usually harder to estimate or determine the state of the robot or the world than to control, say, a certain angle. And so if you come to a situation where the robot isn't working, but it works in simulation, it's not reality that's wrong, it's your simulation that's wrong. And so look back and see what you're missing and go back from there.
Simulations are doomed to succeed.
Exactly, exactly. Number 5, if specs for a part are listed differently in 2 places, they're both wrong. At least one of them has to be wrong, so just assume that they're both wrong. So that means, how can you validate it yourself? Or can you design the robot or algorithm in such a way that you can handle if the motor is actually 500 RPM instead of 600 RPM? So be aware of that and be wary when you get specifications, especially on hobby parts. Number 6, glue, tape, and zip ties are not engineering solutions, though they might work in a pinch.
They're racing solutions.
Corollaries to that, you should be able to open your robot. If you keep on slapping things on, zip tying, gluing, duct taping, then the next corollary, the component that's hardest to access will break first. So always have a plan to be able to open it, disassemble it, replace components, because that will be necessary. Spend the time up front to do it right, and you'll save 10 times the time later on. All right, number 7, do not leave lithium polymer batteries charging unattended. It's just not worth the risk. Use a charging sock. You don't necessarily have to be outdoors, but take precautions. It's worth it. Luckily, this is one I did not have to learn the hard way. So, number 8, always have a complete CAD model, including screws and fasteners, before constructing your robot. Plan out your order of operations for assembly. And so I have this Escher drawing because it's possible, even easy, to draw something in CAD that's impossible to manufacture and or assemble. So as you're designing, keep in mind those questions of manufacturing and assembly. Don't paint yourself into a corner like this. Another corollary is have extra parts on hand, which goes back to being able to open your robot, disassemble it, replace components. When you're ordering parts, order extras now. It'll make life in the future easier. Right, number 9, avoid using slip rings if at all possible. They're a huge pain in the butt. You've got intermittent contact issues, high or variable resistance, or expensive. They can't usually carry a high load. If you can design your way around slip rings, even if you have 2 Bluetooth modules on different parts talking to each other, look into that first. Number 10, clamping collars are always better than set screws. If you have to use set screws though, use a driving flat on steel, hopefully instead of aluminum. Aluminum's really soft. And use an appropriate thread locking agent, some form of Loctite depending on your application. So Servo City, for example, has these clamping hubs that are very easy to, again, install and uninstall in terms of taking things apart and apart. All right, and the last one, number 11, always check polarity before plugging a component into a power source. Not every component is reverse polarity safe, and don't find out the hard way. And the corollary to that, label your battery connectors and components so it's impossible to make a mistake. And so these microDIN connectors, they only plug in one way, but they're not labeled, so you could plug in 2 batteries together. And if they're lithium polymer batteries, that would be really bad. Okay, so that's all I had. Quickly want to thank my advisor and everyone else in the Coordinated Robotics Lab at UCSD, but I'm hoping that we can have some time to talk and hopefully do some questions. Thank you.
So have you heard of single track break codes for encoders?
No, I don't think so.
We'll talk.
Okay.
I don't know why they're not used more. What was your actual involvement in the development of that?
This guy?
This guy. Was that your project?
Yeah, I did the mechanical design, I did the electrical design, I did the programming and the testing.
Another round of applause.
This is a saying that goes along with what he's saying. It's prevalent throughout our companies. We have 5 companies. It's called "Good Enough, Move On," and it's really something we if you stay and engineer it forever, you're not going to get anything out the door, right? So if you want to get out and be an entrepreneur, get stuff out there, get to a point where it's good enough. And that doesn't mean good enough for government work, so give up. It means it's good enough for this phase. You might continue another iteration, but get something, build something, test it.
Right, that's a good point. And on the entrepreneurship side, in terms of developing your MVP, or minimum viable product first, and getting that out and doing market validation, putting something in front of users sooner than later, you're going to get a lot more information and feedback, and it can save yourself time and money.
So Nick, when you were building robots, simulations on the design side, but what was probably the most difficult problem that you ran into in the process of building?
Right. So in this guy, the way the whole thing worked out is that as I was designing it, we were kind of working up against a deadline where we had to deliver a number of robots. And so as I was designing, I was focusing mostly on the first balancing problems and wasn't looking at the edge balancing problem. And then when I later on got on to working on that, I realized that, oh man, there's some design decisions that I would have made differently if I had been thinking about the constraints of this type of problem. And so I was trying to work against some of those decisions I had made earlier, where if I had really planned out and spec'd out, these are the maneuvers, these are the instances, this is how it's exactly going to be used, I would have made different decisions. And so trying to spec that out sooner than later is better, and get into testing before you make a dozen of a type of robot, understand how you're going to use it.
Did you use MATLAB simulations for all your math, and then did you extract the C code from that, or did you have problems extracting the C code and actually making it work?
So I did use MATLAB and Simulink for most of my simulations, and what I tended to do there is in Simulink I had a block that was running embedded MATLAB code, and then I would take that out and put that into this controller board or that controller board or whatever I was working on. And so I didn't use the automatic C code generation, so I had some hand massaging to make sure that variables were instantiated correctly and things like that. I think MATLAB has a handful of specific boards. I think some from TI that they're typically target to support direct deployment and automatic code generation for. And so I think that if you stick to those, you have some chance of success and or
No, you
support.
But speaking from experience,
No, I believe you. I believe you.
you'll still have to go through the massage process.
Yeah.
I think your comment about specking, I think you've done amazing accomplishments with that design, and especially having kicking out the manufacturer turnover. But you know, it was tremendously impressive the first time I saw it, and then when you walk through it and show all the things that it can do, you know, it's pretty amazing accomplishment, right? It's very, very, very remarkable.
Yes.
I have a question just about how long the whole process took and what was the most time-intensive part as well as the front simulation and the building and running it, all that.
Sure. So this project spanned multiple years in different phases, more intense than others. So when I joined the lab in 2009, there was already an earlier version that didn't exactly look like this, but had a similar kind of idea. And so I started working on that one, testing and writing more code for that. And then I came to a point where I really wanted to redesign it from the ground up. So the mechanical design and electrical design was about 10 weeks of maybe half time. And then in the next term, I was working on software design. And then in the spring, I had a group of 5 undergrads, and all of us together did the manufacturing, so the part manufacturing, and then assembly, ordering parts. And that was another 10 weeks. And then the controls problems of this type of maneuver, that type of maneuver kind of came on one by one as I found time to work on it while working on other projects, working on classes and that sort of thing.
So you had a slide earlier about the problems that are facing robotics, which I thought was a really good slide. It did a nice job of explaining the whole thing. I really agree with you that some of those are very, very difficult to solve. The localization and mapping, especially localization, are you planning on working with this robot or with other robots on any of those types of problems, or is that something for another developer?
Right, so my academic research has been mostly on mobility. There have been armies of grad students working on what's called the SLAM problem, or simultaneous localization and mapping problem. And there have been large strides in that using RGB cameras or RGBD systems like the Kinect and laser scanners. There's been a lot of progress on that. And actually that problem of these problems is probably the furthest along, the closest to being solved. There's still multiple corner cases like the Google self-driving cars that you wouldn't want to be in if it's raining, or if there's road construction and what the sensors read don't correlate to the map that it expects to see. And so there's been tremendous progress on that front, but there's still work to be done there.
So are you planning on moving into any of that, or are you just going to stay with mobility? Let me ask it another way. What's your next thing that you're going to take on?
Right, so so I actually just co-founded a startup here in San Diego, and we're still flying under the radar, but we're looking at doing an integrated system.
You're going to solve the green circle that's not showing.
Yes.
I've seen some different mentions of like Arduino and maybe a few other boards. I forget if you said that you've used one particular board in some of these projects. Is there a particular CPU or board that you tend to gravitate towards?
So I've gone around to a bunch of different ones, and it really kind of depends on what you need to get out of it. So on this guy, it's just an Arduino Uno, which is kind of the base model. But it was powerful enough to do what I needed to do, and extremely easy to program, and able to, just reading some analog potentiometers, outputting some PWM for the motor driver, some very simple measuring of signals for the cable detection sensors. It was very easy to pull those parts together. Whereas in a more complex, powerful board that's, say, running Linux, it would take longer to put those pieces together and know that they're running at a high enough rate. This robot is powered by a National Instruments board, the SP Rio 9602. largely in part because National Instruments donated that board and funding for this project, and they bought 6 of these robots, so they wanted it to be using their board. That board is really powerful. It has a PowerPC processor and a 2 million gate FPGA. So I was able to implement some really interesting encoder velocity measurements using that FPGA to measure very low speed. So that was a big advantage to use a board with an FPGA. But FPGAs are really hard to program. They can also be kind of power intensive. And so if you don't need them for that kind of applications, you wouldn't necessarily want to use them.
Thank you very much, Nick. So if you can, so maybe if you can stick around a little bit, maybe people can just continue.
Right, yeah.
Okay, so we have a couple announcements. Firstly, on April 11th, there's gonna be Robot Day at the new Central Library, San Diego Central Library. So I'll be announcing it through our meetup. We are looking for a couple additional presenters and speakers too. So if you have something that you could show for Robot Day, please come talk to me. And we have another really exciting announcement from Ross. So if you can stand up.
Sure.
So